Okay, you may think that's really nice with this kernel trick, but how the beep does this relate to PCA? Well, just a little bit more patient, two slides to just recall what PCA actually does, and then we'll see how we can integrate the kernel trick here into PCA. So first of all, again, PCA using SVD. So just recall that given the data matrix D, SVD computes the following decomposition in these three vectors here. Yeah, for PCA, if you want to compute PCA, we apply this decomposition on the covariance matrix, which is given by D transpose times D. Yeah, the data matrix multiplied by itself, so to say. Yeah, and then we get A here. A transpose, but A consists of k d-dimensional eigenvectors of D. Yeah, if you apply that, then we saw that A actually consists of the eigenvectors of D, yeah, of the original data set. K depends on the rank, so we get in the normal case we get D, but in the general case the rank may be n even. Yeah, but so we need to look for how many columns or rows are actually remaining after a Gauss elimination process, and that may be even n, yeah, because D is an n times D matrix. But since D is a metric space typically, so in with general properties of this matrix D here, it is the case that we have the rank of the rows equals to the rank of the columns. So the rank of this matrix is well defined and restricted to at maximum D. Yeah, and that's what we actually get. We get d-dimensional eigenvectors of the data set D when applying PCA. Yeah? And they are here in this matrix A, and that is the relationship of the features to the concepts. Yeah, and if we have a rank of smaller than D, K, yeah, then we have a relationship of all D features to the K concepts, yeah, and in the general case we have no not K concepts, but we have D concepts actually. Yeah? So that is the so-called worst case, and then the rank is D, and then we have d-dimensional eigenvectors here. Yeah, so that is fine, and that is the general case. That's how this is actually how this is usually working. And analogously here in the O, so S are the corresponding eigenvalues as we know, and O is the relationship between the rows, the observations, to the concepts. Yeah, in the general case we have D concepts, O is a set of K if the rank is smaller than D, but in the general case D n-dimensional eigenvectors, also called eigenvectors here in that case, of D. But this is the relationship between the rows and in these concepts here. Yeah, but we basically look for those two here, S and A transposed. Why is that the case? Because through SVD we get this this decomposition of the covariance matrix sigma, which is computed by the data matrix transpose times itself, and that gives us this, as we saw before, we can reformulate that and see that, we just plug in this decomposition OSA transposed instead of D here, and then reformulate the whole thing, and we end up in a decomposition into A times S squared times A transposed, which is nothing else than our PCA decomposition with the eigenvectors and the eigenvalues here. Yeah, so A or V here in that formula is a matrix of eigenvectors of D, and S squared here is our E, that is the diagonal matrix of the eigenvalues of D. Yeah, so the squared singular values in the singular value decomposition. Yeah, and that is fine, and we can use these eigenvectors here and the eigenvalues especially. So we look at the eigenvalues, we omit the eigenvectors that have low variance or low value, low energy, yeah, and then we can map D onto the new basis, which is spanned by the eigenvectors V here, by just computing this this formula here. Yeah? We just take V transpose times the original data set, and then we get the mapping, yeah? In the new feature space. The mapping is invariant, first of all, against the variance of the data, and if we eliminate D minus K eigenvectors from V, so we only take the K strongest eigenvectors with the highest eigenvalues here for V, we reduce the dimensionality of D here, that should read hat of D, to K, and get a transformation that is optimal with respect to the loss, the total loss of variance. That's how we know PCA actually. Yeah, so that is the mapping, and if we use all eigenvectors, we get a d-dimensional mapping again. So D hat will be d-dimensional again, and if we just eliminate D minus K eigenvectors from V here, we will get a k-dimensional new representation D hat, and we are sure that the loss of variance is minimal with this mapping here, with this transformation. So that is PCA. So have a look at again. We apply SVD here on the covariance matrix which is D transpose times D, and we will get everything what we need. So now, how can we incorporate or integrate the kernel trick? So first of all, once again, the kernel here is defined typically, is defined as the dot product of the corresponding mappings of two observations X and Y, and this original transformation phi here works on the original data, of course. Yeah. So assume that the kernel is known, but the phi is not explicitly given. So as we had it before here, so here the phi, the kernel is given or is known, yeah, but the phi is not explicitly computed. Yeah. So we don't compute actually the three-dimensional case, but we still work on the original two-dimensional data here for the kernel function. Yeah, so the kernel function is known, but the phi is not explicitly given. We don't care about it. Yeah, I mean, we know of course what it is because that defines the kernel function. But anyway, yeah. So now we can compute the so-called kernel matrix, which is just the kernel function applied to all pairs of objects. Yeah, so we get at the first entry. So it's obviously an n times n matrix here because we have the kernel applied to the first object and the first object, then the second first row, second column, kernel of first object, second object, and so on and so on and so on. Yeah, and this kernel matrix, if you take a closer look at it, looks pretty much the same as if we would have applied the phi transformation to our data set and then compute this new representation transposed times itself. Yeah, and that's actually what happens here in the kernel matrix here, obviously. Yeah, so k x1 is nothing else but phi of x1 transpose times phi of x1. Yeah? And k x1 xn is nothing else than phi of x1 transpose times phi of xn. Yeah? So the kernel matrix is nothing else than this one here. And that pretty much looks like the covariance matrix, right? That's exactly true. So the covariance matrix, the original covariance matrix that we used for PCA, which is D transpose times D, is a kernel matrix for the linear kernel, which is just no mapping. Yeah, so phi of x is x. Yeah, so x is mapped on x. So the whole data set is just mapped on itself. That is the so-called linear kernel, so we don't make any mapping. So in other words, in terms of the kernel function here, k of xy is nothing else than x transpose times y transposed. Yeah. So if you get that, that's the halfway through, so to say. Yeah. So the kernel matrix here is just somehow the covariance matrix of the mapped space. Yeah. And the original covariance matrix is of course the special kernel matrix with the linear kernel. Yeah? So and that is actually what we used for PCA. Yeah. So now if we apply SVD on this kernel matrix here instead of just the covariance matrix, well, let's see how far we go.